In this video, we start to learn central limit theory. So this is one of the most powerful theory in the statistical world. So as undergrad student, and we will now dive in further about, hey, why this is going to work, why this theory look like this. But with Therory allow you to first, if you only become practitioner, to do data analysis. So you just need to know, hey, what this theory is about. And the second, we do Therory if you down the road want to get in your master in statistics or master in data science, and then you will able to go further to learn the actual theory, how to prove it. Okay, here we just look at, hey, what is central limit theory and what is the implication of this CLT? Okay, consider the sample mean x bar used to estimate the population mean mu. Our objective is to use the sample distribution of x bar to say something about the population that we are studying. To describe the sample distribution, we need to know the mean, variance, and the shape of distribution, as we already discussed in the previous chapter. Anytime talking about how your sample look like, you need to talk about the central location, variability, and also the shape distribution. So therefore, when we consider the x bar as a sample as a random variable, and we need to understand, hey, for this random variable, what is mean, what is the variance, and how the shape of distribution should look like. So as long as our sample are randomly sampled, the only type of error we will have in our estimating process is the only sampling error, which means every time we go back, we might get different numbers that causing us getting the mean of the x bar are look different every time, and they also look different from the population mean. So the sampling error of the sample mean is described by the standard deviation. So this value has a special name called the standard error of the mean. Okay, now let me recap what we're talking about here. Okay, remember at the beginning of this chapter we said sample distribution is focusing on looking at the mean of the statistic and the standard deviation of the statistic, but we don't want to call that the mean of the mean, the standard deviation of the mean, because it's confusing. So we're creating a new term. So the mean of the mean we call expected value of the mean. And when we're looking at the standard deviation of the mean, instead of called standard deviation of the mean, we call the standard error of the mean. So we just try to creating a new term so that we are not confuse ourselves. But also, it does increasing some creating some memorization load on your brain. So you need to remember, hey, standard error of the mean, that means the standard deviation of the statistic mean. So how can we calculating the standard error? Standard error of the mean. So the standard error of the mean is denoted by sigma x bar x bar. So it's very important that when you write down the sigma, you don't forget about the subscript x bar, because this standard deviation is designated for my sample mean. So without this x bar, you are talking about our population data's standard deviation. Okay, so therefore, the standard deviation of the mean, we call the standard error of the mean, is equal to the the population standard deviation from your data divided by the square root of n. Okay, again, we are not go diving in terms of how this formula coming from. So this is going to be the formula you're going to use to help you calculate the standard error of the mean, which is the standard deviation of the mean. Okay, standard error of the mean. And so as you notice that for this calculation, if your sample size go up, so the n is getting larger and larger, the ratio, so this ratio will get smaller and smaller, right? So therefore, at the standard error of the mean decrease as the sample size increases. So what does that mean? That means if your sample size get larger and larger, and the variation of the sample mean will become smaller and smaller, and you can imagine get it extremely large, so the sigma x bar might become 0. So that means your sample mean become your population mean, right? Because the variation disappeared. Yeah. So this is a relationship. So first, before we move on, I want to show you an example in terms of how you are able to leveraging this formula to calculate the standard error of the mean. So let's see, given the average spending by a salon customer for facial treatment is mu equal to $80. So since we're using the mu, this $80 is representing my population. And with the standard deviation sigma equal to $10. So then the standard error of the mean for a random sample of 20 facial treatment is what? So to calculating this, since we not focusing on the population, we look at, hey, I got this 20 people, we got it. We try to understand, hey, for this 20 people, and then for this sample with 20 facial treatment, what is its standard deviation should look like. So to answer that question, we're looking for sigma x bar, and it is equal to, follow the formula, we use a population standard deviation, which is 10, and divide by the square root of n. N is 20, so that gives us 2.236. So that is the standard deviation or standard error of the mean, so which is much smaller than the standard deviation of the population, right? So that's pretty straightforward, because if you think about this standard deviation is not about the population value anymore. It is about, for this sample of 20, and we calculate its mean, and I go back to collect another 20, we calculate its mean. So this standard error, we are looking for that standard deviation for the mean's standard deviation, right? So therefore, it's the standard error of the mean. So it's much smaller. So if the population is normal, the sample mean has a normal distribution centered at the mu with the standard error of the sigma divided by square root of the n. So as the sample size n increase, the distribution of the sample mean converges to population mean as the standard error of the mean getting smaller. Okay, so what we try to say is that instead of 20 facial, in the last example, instead of 20, let's increase to 1,000. So you will notice that the sigma divided by square root of n will get smaller. That means your sample mean x bar will getting closer. The sample distribution will getting narrower towards in the value of the mu. That means you are reducing the variability of your sample mean, and that will become getting closer to your population mean. Okay. So, however, the population may not have a normal distribution, or we may simply not know what the population distribution look like. So what we're gonna do, so here is where the central limit theory will play a role. So for the central limit theory for a mean, is that if a random sample of size n is drawn from a population with a mean equal to mu and population standard deviation to sigma, the distribution of the sample mean x bar approach to a normal distribution with the mean equal to mu and the standard deviation equal to sigma divided by square root of n as the sample size increase. So basically, central limit theory is saying, regardless whether your original population follow normal or not, if your sample size is large enough, we are assuming it's going to be follow a normal distribution as well. So that is what central limit theory is saying. Don't worry about distribution you're facing. If you have larger sample size, we pretty much can assume it is follow normal distribution. Okay, as you can see on this diagram, whether it's already a normal or it's a uniform or it's a skewed distribution, if your sample size is large enough, and we believe it will your sample distribution will become normal distribution. Okay, you just need to make sure your sample size is large enough. So that's why there is a saying, if your sample size is large enough, everything become normal. Okay, if your sample size is large enough, everything become normal. That is what the central limit theory trying to explaining is. You just need to make sure you have larger sample size, and we can assume it's follow normal distribution. Again, we are not diving further how to prove this theory will be hold, because that will be the task for your master degree we're focusing on if you're getting master statistic or master in data science. Okay, so here we're going to talking about when we consider the sample size large enough. A rule of thumb is that 30. So the 30 is the minimum sample size you want to have in order to have to assume the data is follow normal distribution. However, if you know your data is symmetric, and then sample size can be smaller than 30. So for instance, on these two diagram, so for the first called uniform population means if you look at it, basically it's a rectangle. So that is a symmetric. Okay, so let's say here is a 0, your left hand side, right hand side will be the same. So therefore, if it's a symmetric distribution, you don't really need 30, less than 30 observation in order to assume your data follow normal distribution. However, if your data is a skewed distribution like this, highly skewed to the right, in order to assume this kind of distribution is a normal, your sample size should really meeting that 30 requirement, at least 30 observation, in order to assume your sample distribution is follow normal distribution. Okay, so now after we know what is the sample distribution, what is the central limit theory, what the central limit theory are doing, let's talk about the range of the sample mean. The central limit theory permits us to define an interval within which the sample mean are expected to fall. As long as the sample size n is large enough, we can use the normal distribution regardless of the population shape. So what is the use case here? Some students are going to ask. Right, so we first understand, hey, what is the population? And then we start to thinking about, we understand what is sample distribution means. Sample distribution means it is the distribution of my statistic. It means instead of just thinking about one sample, I'm go back to my population to sampling many, many times. Each time I sample exactly same sample size amount, and then we calculate that statistic. The sample distribution is focusing on that statistic, how that statistics distribution look like. So therefore, the use case for range of the sample mean is that given you know the information about your population, we just try to understand, hey, if this is my sample size, and what is the potential range for my sample mean? So for instance, in that GMAT example, in the previous lecture, let me go back. Okay, so let's say this example, right? So here I only did 8 samples. So, but each sample I only have 5 observations. I did 8 samples. So as you know, it's kind of costly for you to keep going back, getting 5 sample. Is there any way mathematically I can just say, hey, regardless, if I get 1,000 sample, each sample have 5 observations, what is my sample mean distribution should look like? What is the potential range should look like, right? So that is what we mean by the range of the sample mean. We want to understand what is the potential range for the sample mean. Let's say I did 100 samples. So among these all 100 samples with a certain confidence, what is the potential range for that X bars value? Okay. So to answer that question, we are looking at this formula. So the expected range of the sample mean is equal to mu. Again, we already know the population information, right? So the mu plus minus the z statistic times the population standard deviation divided by square root of n. So as you know, sigma divided by square root of n is the standard error of the mean. So mu is the population mean, and the plus minus the z, we're going to spend a little bit of time to explaining what is the z. So z score. And so since it's a range, we have lower boundary and upper boundary. So when you use the minus sign to calculate this equation, that gives me the lower boundary. When I pick the plus sign, that gives me the upper boundary of this range. So let's look at example together. Okay. So for the z-score, the z value is coming from the standard normal distribution. Okay, the standard normal distribution. The reason is that we already said if our sample size large enough, we consider the data, the sample distribution is follow normal distribution. And for the normal distribution, if we standardize it, and it will become the standard normal, and it will be coming from, we will be able to obtain this z value. Okay, so therefore we're using this z value. And here we are showing 3 scenarios when z are different. So when we're looking for 90% intervals, the z value we use is 1.645. When we look at a 95% interval, the z value we use is 1.960. When we look at the 99% interval, confidence interval, and we're using 2576. Okay, so depends on how wide that interval we're looking for, that z value will change. But you can imagine that 90% interval, which is like relatively narrower, because you can think about if it's a 99% interval, what is the 99% interval? It will become wider and wider, right? From 90% to 99%, that range will become wider and wider. So therefore, my z-score here is getting larger and larger. Okay, so in the computer skill lecture, I will explaining how, actually in next video, we are explaining how those numbers are obtained. So again, it's the z value, and so we are actually can use Excel to getting those numbers versus you just memorize it. Okay, so given the 3 formulas, let's work on a problem together. Okay, so the amount of liquid in a half-liter bottle of the Diet Coke is normally distributed with a mu equal to 505 milliliter, sigma equal to 1.2 milliliter. So now we know the population information about the liquid the liquid in the half-liter bottle, right? So they are not exactly 500 milliliter. So there were some variations. So the mean actually equal to 505 and the sigma equal to 1.2. Because the population is normal, and then the sample mean x bar will be a normal distribution, normally distributed random variable for any sample size. Again, so if the population is not follow normal, and we need to check on the population distribution. If it's skewed to the right, we need to make sure the sample size will at least 30. If it's symmetric, we can maybe consider 10 or 12 be good enough. But since the original population is follow the normal distribution, and we don't need to worry about my sample size to apply the central limit theory. Okay, so if we sample a single bottle, so therefore we have this confidence even sample size equal to 1 is supposed to also follow normal distribution. And the measure is field. The sample mean is just x, which should lie within the range shown in the table below. Okay, we're going to show you how to calculate this range. And later on I decide instead of n equal to 1, I want to do n equal to 4. And also we want to figure out, hey, what is the range for my sample mean if n equal to 4. So to apply the formula we just learned, so here instead of use 90% range or 99%, I pick the middle one, 95% range of the sample mean. So therefore, I'm applying to the middle formula here. The z-score, a z-value I'm using is 1.96. Okay, so when the sample size n equal to 1, and then so I'm going to replacing the parameter value with the value we already given. So the mu equal to 505. And then plus minus 1.96 times here should be sigma. There is the typo, not alpha. Sigma equal to 1.2 and divide by square root of n because the sample size in the first example, we only have 1. And then so we further calculate and I'm able to get in this range. So when I use 505 minus 2.352, okay, I'm missing a decimal place here, 2.352, I'm able to obtain 502.6. When I use 505 plus 2.352, and I'm able to get in 507. And now I'm able to use the 505 minus 2.357 to get 507.4. Okay, so that is when n equal to 1. When n equal to 4, I'm replacing the n by 4, and I'm able to get in this range 503.8 to 506.2. Okay, so instead of, so I'm able to directly using the formula to calculate the 95% range for my sample means, right? So what's going to be the alternative? Alternative means you're going to go back to sample many times. So for instance, you're going to sample 1,000 times to actually see, hey, for approximately how many, in order to get in 900 among my 950 of the samples, what is the range should look like. So that is how we are interpreting this 95% range of the sample mean, right? So if we look at when the sample size equal to 1, so that means if we took 1,000 samples, so for each sample we only have 1 data point. Okay, we go back 1,000 times, each one we only grab 1 bottle, and we compute a mean, and we would expect approximately 950 samples mean would align within 502.6 to 507.4. Okay, similarly for the second scenario, let's say I go back to look for 1,000 samples, each sample have 4 bottles, and I'm computing each 4 samples sample mean, and then expect the value, we are expect that approximately 950 of the sample means will line between 503.8 to 506.2. Okay, so that is how you are interpreting this range of the sample mean. Okay, so luckily we have this formula, therefore we no longer need to go back 1,000 times to do that experiment. We can just rely on this formula to help us understand, hey, what is the range of my sample means? So again, we are now learn how to prove this formula. That will be a next level of the learning in your master degree. Here we just need to learn, hey, how to use this formula. Hey, what does this formula mean? And how to interpreting the result from this formula. Okay, so in our next video, we're going to start looking at our confidence interval.